how's it going? Yeah, I'm glad that I came second here because I think I can dive a little bit deeper into this topic and maybe provide you some extra information to maybe help you think about these problems. In general, particularly right now in Erlang Elixir, I'm seeing quite often people are encountering the issue of I want to scale my system up horizontally or have multiple nodes in a system and are surprised to find out that despite how easy it is to write a concurrent program in Erlang Elixir, the primitives are in the beam, but there's not a whole lot of high-level tools to help you solve the problem of replicating state across the system. So one of the best quotes I've read in recent history about this, I think sort of encompasses a lot of this. One of the difficult truths of large-scale systems or services is that if something can go wrong, it eventually will. So correspondingly, it means if you're writing a fault-tolerant system, then you need to be prepared for this. You need to be making sure that you're testing the things that can go wrong to see how the system fails, and then figure out what you need to do to cope with that. So typically the need for distributed state arises because you now need to either scale either for reliability, so you have some redundancy, maybe you want more nodes in the system for performance, you want memory in state perhaps so that reads are really fast, but that then induces this situation where you need to have your data replicated in memory across multiple nodes. Sometimes it's for both. And the assumption is that this data is almost always accessed simultaneously by different clients. Sometimes those clients are other servers themselves. Sometimes it's actually, like a client program, a CLI or something like that, connecting. So normally the way that this happens, you start with like your single node application. You're just building a system from scratch and you start small, feeling like you'll solve this problem when you get big. You reach that point. So you decide you're going to split your system across multiple nodes, maybe just simple replication, but you might also run some set of applications on one node, some set on another. And what you first find out is that some of the solutions you can rely on when you're running a single node don't apply or not directly apply to a multi-node system. Namely, the use of ETS, which means if you had a shared table that you're expecting processes to read from, that's not going to work across nodes. So now you have a situation where you have a table that you need on both nodes, or you need a way to communicate to that one table from all the nodes in the system. Registry is similar. It's based on ETS, so correspondingly, if you've got registered names in your system that you need to read from different nodes, registry won't solve that problem for you. So you either need to have some sort of replication for registry or use a different registry. This problem may be getting solved at some point. I'm not super up to date on what the core team's thoughts are on that, but this is a problem that you may likely run into. And then you got other things as well, like singleton services in particular. You probably use registered names, like use registry for that kind of thing, but now you need a way to communicate across nodes to find those things, which again gives you this issue of service discovery, right, which you're probably using registry for or something similar, but now you're in a replicated stateful situation. These are a few of the use cases that you typically want to use some kind of distributed state for, right? So again, the global process registry or service registry. You've got a cache that's sort of like the ETS-based table thing where you got to replicate across systems. Locks to acquire mutex on something that is sensitive or critical. Presence, which I'm sure a lot of you are familiar with if you've been playing around with Phoenix. There are some built-in tools for this in Beam that we're all kind of familiar with to some degree or another, maybe just heard about it, but Global solves kind of the process registry and locking situation. And Amnesia is kind of like your distributed ETS with some additional functionality on top. Something that resembles a little bit more of a traditional database in that you've got schemas, but it also solves this question of like, how do I get data in this table across all my nodes without necessarily having to do all that by hand? The problem is that these tools are not necessarily the right solution or maybe don't cover the problem entirely, but they're good out-of-the-box things to try and use. An example of what I mean by why this is not necessarily the greatest tool to use is kind of demonstrated by amnesia, where if your nodes get partitioned, and by partition I mean, between each other they lose sight of each other. So a node doesn't necessarily crash or go down, but maybe a network route gets misconfigured, or the host network card fails or something like that, and no longer are able to see each other. When this happens, you can get in a situation where writes occurring on multiple partitions are both accepted. And this is referred to as a split brain situation. And then recovering from that situation once you have a split brain means that you have to choose writes on one side or the other that you're going to essentially abandon. So you'll lose data as a result of trying to fix this after it's happened. So you want to avoid it to begin with. And a specific example of a situation where this can happen in a way that is really bad is this that I've kind of demonstrated here. Power failure takes down both the nodes, and in the process, the disk on one of those nodes dies. The last node is going to wait for its partner to come back, but it never is going to, and it can't be recovered. With amnesia, you can actually configure a timeout to say, like, after so-and-so time, just ignore that node is gone, we'll just resume where we left off. But if you don't configure that timeout, it will just hang indefinitely. But if you do, and that node doesn't come back in time, which it won't because the disk is gone, the transaction recovery process is going to drop data that should have been recovered. Or it might, it's not guaranteed. It depends on your usage pattern and the data that you're storing in there, but it's the possibility of failure that you have to account for. And if this happens, it can kill the node as well, depending on how you corrupt the data that's stored in amnesia. Excuse me. So to kind of add on to some of the questions in the last talk, here's some things that are more specific to how you're going to cope with distributed state. So if you have multiple readers and writers, how are you going to deal with conflicting writes? What guarantees must clients reading and writing data from the system, what do they need to observe? And by observe, I mean, like, if I write some key and then read that value, what am I going to get back? Is it going to be the same value? Is it going to be something different? Will I see something in the past? You also have to be able to ask, do I, as a client, connect always to the same node? Can I write or read from any node? What are the performance implications of that? If everybody's talking to a single node, it's going to be slower. It also implies that you've got node-to-node communication between the leader and any replicas. That's where kind of the performance overhead of Raft and similar algorithms comes from, is that there's more coordination going on. But in an eventually consistent system where everybody can read and write from arbitrary nodes, you abandon that performance overhead, but you incur a different problem, which we'll get to in a bit. So data has to be replicated. How's that going to happen? Like, what's the protocol for exchanging the data across nodes? How do we keep that consistent? How do you resolve conflicts again? And in particular with partitions, how does that impact the system? Do we lose availability, or do we risk becoming inconsistent for some period of time or maybe indefinitely? And how do you recover from various different kinds of failures? Like, if your disk goes, is that recoverable? If you just reboot, how do you deal with, like, going down, losing data in memory and coming back up? How do you deal with, like, different lengths of time with a split brain or, like, partition network? Do you time out, or you just wait until things come back? All of those decisions impact either availability or consistency. Here's some assumptions in particular that will burn you when you're asking about, or when you're designing a system that has distributed state involved. Time in particular, I've seen a lot of people make the assumption that clocks are close enough, or that they can use NTP to sync the time on all the nodes. Time is completely unreliable when it comes to distributed state. Do not make any assumptions about it. It's useful as like a general like metadata kind of thing. Storing the times at which things occurred can help you troubleshoot issues, but it's not useful to actually rely on as an algorithm. Even projects like Spanner, which have a whole bunch of fancy tech around synchronizing time on a global scale, have their limitations. In particular, one of the major limitations is that there's like a space of time in which things have to wait for operations to actually commit, and that's a huge amount of overhead for typical cases, but is acceptable in the case of Spanner. But even then, they allow this wiggle room of like, well, in certain situations, like this is not going to be perfect. Again, network redundancy. You might assume that my network is heavily redundant. I'm not worried at all about this being a problem, but it's not the only way in which Beam systems can get partitioned. The most common way to see this is with the RPC mechanism. In the Beam, this occurs with a single process on every node, unless you use an alternative distribution protocol, but the default is a single process. If you're doing a lot of cross-node RPC, you can actually overload this process, and heartbeats between the nodes that keep them alive in each other's eyes also use this RPC mechanism. If you overload this, those heartbeats can extend, like take too long to arrive at the other nodes, and cause the other nodes in the system to think that you've disconnected or lost your network. So you have a partition, even if it's brief, but it's there. Assuming that messages will always occur in the same order. Like there are some rules that you can follow, but in general, it's better to assume that it is possible for messages to arrive out of order. Particularly in the Beam, there's no guarantees made whatsoever that messages sent to another node will arrive in the order that you send them. It explicitly calls that out in the document or in the documentation. So if you assume that they will arrive in that order, that can also cause some problems. And with synchronized data replication protocols, it is absolutely essential that you don't bake these kind of issues into the algorithm you're using, because it will bite you later. And then it will be very difficult to either recover from or even figure out what went wrong to begin with. Your file system is also unreliable. I mean, in the general case, file systems can help, like ZFS, that kind of thing, where you've got checksumming and some sort of redundancy at the file system level. But even then, disks can get corrupted, they can fail entirely. It's better to assume that you need some kind of redundancy even at the file system level, in your algorithm, I mean. And then there's situations where like really sort of edge case kind of things can happen, like what I write up here. Your host powers on and powers off really fast, multiple times. I watched a demonstration of Foundation DB where they did this with a cluster of like 3 or 5 nodes on like Raspberry Pis. They booted them all up, and then they just sat there and flipped the switch on and off to demonstrate that Foundation DB had like solved this problem, right? That they was able to cope with it. But the reality is that most systems will not cope with that well. So a couple of simple examples of the kind of thing that you could bake into your system without really thinking about it is, you've got a client of a GIN server you call, and your connection gets disrupted somehow. Either client to server gets lost or server to server gets lost. But the client now needs to make a decision about how to deal with that. Typically what we do is bake in some kind of retry, right? So the client will retry that request. But if what happened is that the server actually got it, but before a reply made it back to the client, the connection was dropped, that means you're going to have sent that request twice to that server, and the client's not going to be aware of that. And if your server's not dealing with that, you might have committed data twice. The trivial example would be a counter, right? If you increment a counter twice when you should have only incremented it once, that's a problem. It's kind of a naive point, but hopefully it's kind of clear why that might be an issue. Another one would be if a server is blocking, it's trying to behave synchronously, waiting for an acknowledgement of a write that it's trying to commit. if the server that it's talking to or the other end of the connection just never responds, now you've got a deadlock. And that can cause downstream problems, maybe even data loss if the system itself starts to get overloaded and crash. Leader election with dynamic node membership is one that I'm still trying to find a good solution for. But in particular with Raft, one of the things that is an extension of the protocol is how to arrange nodes to come into the system and to leave. And it does not allow you to just join arbitrary nodes and have them leave, because the problem is that if in a situation where you have a network partition, nodes can come and go, there's no way to distinguish from the leader's perspective whether or not a replica parted because it just was done, it was shutting down, or because of a partition. You're forced to treat it as the same thing, but if the other side of the partition assumes like, oh, well, those other nodes left, we need to elect a new leader. Now you can have different leaders on different sides of the partition. Then you got conflicting rights, and again, sort of the amnesia problem that I described earlier, where you have to figure out how to recover from that by throwing away data most of the time. So the main question for me is like, how do we actually test these things? How do I build a protocol for replication, or maybe not even a protocol? How do I build a system that's going to use maybe somebody else's library that implements a protocol? How do I test and verify that my system behaves the way I want it to under these kinds of faults or different kinds of issues that can occur? In particular, if you're the one implementing some kind of fault tolerance protocol, it's super easy to think that you've done it right, handled all the edge cases that matter, and you've made some assumptions about the runtime environment that just aren't true. Maybe you're following an algorithm you found in a paper where they call out explicitly like, we're building this under the assumption of like no message loss can occur, or like no message delays or something like that. If you overlook that and just follow the implementation of that algorithm, now when you're running an environment where message loss or reordering or delays or whatever is possible, you're gonna have a problem. Like your system's not gonna uphold the guarantees that you're telling people that you're trying to uphold. Very, very common issue actually. So fundamentally, we just need a way to verify both the protocol and the things that we build on top, because composition of these things matters too. There's a couple definitions that I've mentioned, or were mentioned in the last talk, that I think are important to clarify, right? So the question of these three things: consistency, availability, and convergence. Convergence is probably a new one for a lot of you, but I'll explain what that's all about here in a second. But the two at the bottom are liveness properties. That means, how does my system respond to various operations like reads? But consistency is the one that we really care about, and that's the question of safety. So consistency, succinctly as I can put it, is it constrains the order in which reads and writes appear to occur from either a client or a server's perspective. You have to ask from both because it depends on what matters for the protocol. Availability is, to what degree do reads and writes, are they allowed to occur under different kinds of fault tolerance scenarios? So in a partition, does my system remain available, or do I not respond to any reads or writes until the system recovers from that partition? Convergence is really kind of the trade-off between the two. So convergence describes what happens when data is replicated, like at what point does it become consistent? As I put it here, defines to what degree connected nodes are required to observe each other's updates. But really what matters is like, when does my system become consistent? Does it ever? And that is a trade-off between availability and consistency. The more available your system is, then under certain classes of failures, you can't converge right away. It's just not possible. This is, well, I'll get to it in a minute here. I think there's maybe something that will help explain convergence a little bit better. So more precisely, consistency is described in terms of a test of properties that that consistency model is supposed to uphold under an execution. And what execution is is like a set of nodes, like I've got 5 nodes, and then a sequence of read-write operations against one or more of those nodes from either a client's perspective or just node to node. And then the properties that usually are included in that trace would be the node that an operation occurs on, the key and value involved, and the start and the end time of that operation. And then for reads, it's the same thing, except for you also get a list of the writes that were that produced the value that was read. This information allows you to test all sorts of variety of properties about the reads and writes that happen, about the consistency properties that are there. This is the foundation upon which a consistency model is kind of defined. So something is consistent under some model if all the properties that are described by the tests pass against that execution, some arbitrary execution. So a trivial example would be like, I have nodes A, B, and C, and some client, and I issue, 3 writes, a read, 2 more writes to different nodes, another read. What does the client see when it performs that last read? That would be like an execution scenario that you would then test these properties under. So there's a variety of consistency models from like a server-to-server protocol, right? So we're talking about replication here, not involving a client. Weak is basically no guarantees whatsoever. Eventual is more of a statement about convergence. This is what I kind of meant about circling back on that. Eventual consistency isn't really a consistency model. What we're really saying, or trying to express when we say eventual consistency, is that eventually my system will converge on a single shared view. So reading the same key on all the nodes will produce the same value. Causal consistency is kind of a tricky one, maybe new to you, but the way that this works is that all the reads and writes that occur in that execution have a partial order, meaning that if you try to stack them up, they have some order relative to each other. And usually this is in the context of a single node. So you can have reads and writes that occur concurrently, but there is some kind of happens before relation between reads and writes, or between 2 sets of, or a pair of operations, right? Let me see if I can describe this a little bit more precisely. Yeah, so basically if it guarantees that on some node, a read will always return a value which represents all the writes which occur before that read, relative to that partial order. And usually the thing that we care about with regards to partial order is if I as a client do a write and then a read, I'm going to expect that the read produces the write that I committed. There are more, it's like very abstract kind of thing, but the idea is that there's some kind of causal history that imposes an order on things that occur in the system. And causal plus is an extension of that so that it reflects the real-time order in which operations occur. And by real-time, I mean actual, from your perspective, wall clock time. From the algorithm's point of view, that's not true because, again, like I said earlier, time is irrelevant to this. But there is some sort of sense of real time with the system. Essentially, in Causal Plus, it is impossible to ever observe something that has the appearance of time moving backwards. So you can't like write something twice and read and then observe a written value that occurred before your writes. That would be a violation of that consistency model. The remainder of these are somewhat familiar from database terminology. Serializability guarantees that all operations in a system have a total order, which means that there's no pair of operations which don't have some kind of like this came before that. But it doesn't necessarily mean that the ordering that is present reflects real-time ordering of things. It's basically up to the algorithm to decide how things get ordered out, but once that order is decided, that will always be the same from every node's perspective. Linearizability is like a stronger guarantee, but is really defined in terms of a single key. So generally when we're talking about consistency, we're talking about like the system as a whole. Linearizability is like a more specific property. This is a thing that you normally intuitively expect like a perfect system would hold, right? So if you have concurrent reads and writes, linearizability would say that the real-time order in which those things happen is going to be the order in which they're observed to happen. But it's specific to a single key value pair. The stronger version of that, which is a little bit confusing because of the naming, is strict serializability. This is like linearizability in terms of the entire system, essentially. Everything has like a total order, and that total order reflects the real-time order in which things happen. And the strongest, or like a weakening of strict serializability, which is a little bit more realistic, is sequential consistency. So this means that the real-time constraint is relaxed, but all transactions do have a total order, and all the processes, all the nodes in the cluster share that same view. So that's a lot to try and process, but hopefully that gives you a general like gut feel of the relative order of these things. I kind of put these in order of weakest to strongest. So if you're evaluating a system and these terms are being thrown around, this is kind of how you can intuitively think about them. But I encourage you to like really read the definitions to truly understand the properties involved here, because my quick, dirty, like gut reaction to defining things is not great. An extension of this is with client-oriented consistency models. This means like I'm not sure that I care so much about how things appear to nodes in the system, but as a client of the system, I care about these properties. And they have slightly different names. This is the monotonic reads, writes, read to writes, and writes follow reads, which I don't know why they named those so much better than these other ones here on the left, but there you have it. Monotonic reads and writes is maybe a little bit confusing, but essentially the idea is that in terms of time, reads or writes will appear to move forward only. It can never move backwards. So with reads, it means if you perform a read of a key and then perform another read of that key, your second read will never observe a value that's older than the value you got from the first read. And writes is similar, but with regard to writes, where once you write something, a read can never read an older value than what was written. Read writes is, I wrote this down because I want to be very specific. For any write and any read, if the write falls before the read relative to your client session, then that write has to be visible to the read. So this is like encompassing the idea of I write something and then read it, I should get the value that I wrote. Or something that occurred after my write, but I will never see something older than that. And then writes follow reads is, once you've read something, you can't change the past. So again, like I said, like if you write and then read and then write, the first write always has to appear to yourself or as the client to have occurred before the second write. So it's a lot to process, but again, hopefully that just gives you sort of an intuitive understanding of the different trade-offs that you can make, or properties that you need to be able to express in order to say, my system upholds this consistency model. So availability defines the ability of the system to actually observe reads and writes, or more precisely, that they complete. So if, as a client, I perform a read or a write, completion means like I get a response that says like, here's the value that you asked me to get for you, or yes, I wrote that value. And it's expressed in terms of the conditions under which availability holds, right? So my system is available under network partitions. That would mean then that you can have divergent writes on different partitions, but it means that your system will respond more often than it would in a system where when a network partition occurs, I'm not available. Leadership change is another good example. Like this is a thing where, in particular, like Raft will not respond to reads or writes until leadership election has resolved a new leader. there's these three kind of extra terms I threw in here. They're sort of intuitions around availability. So always available means what it says. My system always will respond. Sticky available means like as a client, if I'm always connected to the same server, the system will remain available. So this would be like in a network partition scenario, if I'm talking to the same server I was talking to before the partition occurred, the system appears whole to me. And quorum available means the system remains available as long as some subset of nodes is available to me, or at least to the side of a partition that I'm talking to. So back to convergence again. Here's a little bit more detail around this. So the ability to ensure that writes are observed on all the other nodes is ultimately what's important here, because the implication is that it should produce the same value on all nodes in the system at the end, if a system is convergent. So fundamentally, in a system with distributed state, you need to have defined these three properties with regards to your solution to your replication issue or whatever the distributed state, the shape of that takes. You have to be able to express these guarantees and they must be upheld. And so you need a way to test that. And so what we really need, and we don't have today, at least my opinion, is foundational tooling for this kind of thing. How do I express the way in which I want to solve this and then actually test that these properties are upheld? So we need a way for testing that our replication abstractions actually behave correctly under real-world faults. And that is very difficult to test using your primitives that you just have in any programming language, because it doesn't let you test what happens when my disk explodes, what happens when the node restarts 5 times, things of that nature. And we don't really have any fundamental tools that allow fault injection either, even for simple things so like this message gets dropped. You can build that kind of thing in yourself, but it's not something that's there. And in particular with the beam, there's no way to, at the VM level, say, drop every other message or something of that type. You need something that kind of wraps the beam to do that for you. And we need a way to also test the things that we build with this, right? When you compose a couple libraries, one that maybe solves your replication protocol, and then on top of that, you're building like a process registry, you need a way to say that when I combine these two things, the way the system behaves is actually what I thought was going to happen. And that's even harder, right? Because your library, for one, might give you some ways to test its behavior, but it doesn't necessarily give you a way to test what is built on top. I have an example here, right, of you might have a process registry or a cache or something where you want it to have one consistency model in one part of your application, but a different consistency model in a different part for trade-offs maybe related to performance or reliability, whatever, it doesn't matter. But the point is, why should there be two separate libraries for something that's logically the same, right? You've got a cache. The behavior of a cache doesn't change under different consistency models. It's just what values you get back based on writes and things like that that change. And that shouldn't be visible to a process registry. The process registry implementation shouldn't care about those things, at least to a certain degree, right? Like maybe some hooks to say like, well, when a write gets resolved in a certain way, like I'm gonna change something or like notify some processes. That is like a higher level concern, but fundamentally they shouldn't be dealing with like replication. So I started work this last fall. I've been kind of diverted onto some other things recently, but it's very close to being done. I just have to wrap up a few things, find some time to do it. But this library is called Cadre, and it is really intended to provide all of this that I'm talking about: the foundational tooling, test framework, abstractions for being able to inject different kinds of failures, basically any kind of failure you want, and then essentially a model checking approach to verifying the system under these different kind of faults. And you can have it inject any sort of combination of faults. It doesn't really matter. So there's basically a simulation framework with abstractions that you wire your higher level implementation on. So to use the process registry example, you would use the abstractions for node-to-node communication, for persisting state, and then for the consistency model that registry is going to consume. And the way that's exposed is really in terms of like primitive operations like reads or writes. But the point is that all the things that are non-deterministic in the system have abstractions so that they can be made deterministic under simulation. The way it works fundamentally is it's a type of simulation called discrete event simulation, which means that the system is stepped forward in time, and at each step, things are allowed to happen. But the way that things happen is always the same. But you can inject sort of randomization into that by saying, like, okay, I have some seed, and then based on that seed, I generate like some subset of random faults, and then inject those at different points in time throughout the execution. But if I want to maybe tweak the code a little bit to fix an issue that was identified and then rerun it, I can choose the same seed and get the exact same execution and be able to verify that like the thing that I thought I fixed actually got fixed. Which is a key way of testing this stuff, is not just can I verify the system, but how do I fix problems I discover in the process? One of the things that it provides beyond just those pluggable implementations for different parts of that, namely, how do I persist data? How do I talk to other nodes? How do I verify consistency? Fundamentally, like the underlying layers are based on some assumptions, particularly the persistence layer, which is based, it follows Foundation DB's style of using an ordered key value store set of semantics. What that gives you is really fast, like range reads, the ability to construct indexes, higher level things that the persistence layer doesn't need to care about, but you can build on top. And then from the perspective of like a process registry, I don't have to care about those things, but I can choose which layers I want to use with my process registry when I'm putting it all together in a real system. So people can write libraries that change how persistence is done, like whether it's on disk or in memory, or how do nodes communicate with each other? Do they use Raft? Do they use Paxos? Do they use something else? Do they use some form of eventual consistency? It doesn't matter. I can pick and choose that stuff at runtime. Even inject it as like different things for test and dev, however you want to use it. It's built on that very pluggable model. And underlying all that in Cadre is this concept of like a driver, which knows about these abstractions and knows how to move the system through different steps that it needs. The driver only applies when you're running the simulation framework. At runtime with Cadre, none of that overhead is there. It's only there during test. But the point is that I can run a set of property tests, for example, that use this simulation framework, and the driver handles swapping out all the normal communication mechanisms, using all the things that it needs to trace execution through the system. So it needs to know when A talks to B, what the message was, when that was sent, what the data was in that, and then it uses all that to build like this trace log of everything that happened during execution. And then that is converted into a structure that's easy to analyze statically. So one of the main features of that execution trace is that we can then use that to provide lineage and counterexamples when a test fails. So a test is described in terms of like pre and post conditions that need to hold. So given X, then Y. If those either pre or post is violated, then counterexamples are produced that show like, well, when X is this, Y is not what you thought it was going to be. And then that also allows you to produce a lineage graph that says, okay, at the end of all of this execution, key X had value Z, and this is how we got to Z for that value. Like this is the series of operations that led to that. And I kind of talked about a little bit this already here with the composition of things. But the key, right, is that as a developer, I don't need to be an expert on Raft or something like that. nobody has the time to understand that stuff. I know Keithley spent like a boatload of time on his Raft library. I spent, I don't know how long reading about it without bothering to implement it myself. But not just Raft, like a bunch of things. It just takes so much time. The papers are dense. They're full of like, mathematical notation or computer science notation that can be really hard to parse if you're not, educated in reading those kind of papers. And even then, like the syntax between papers is different sometimes. It's like a whole world of pain that you shouldn't have to deal with. You should just know that like Raft is perfect for my use case because I know that it has these guarantees that it upholds, and so I'm going to use like a Raft consistency model for this particular problem I'm solving. Yeah. You shouldn't also need to like reinvent a test harness and framework for something that somebody's already done. And that's part of the problem, is that because there's no way to test things in composition, you have to rewrite all the possible tests to examine how faults affect the system. And that's really difficult. It's really easy to miss things or set up tests that you think are producing like a favorable result when it's really just your test is wrong. You don't want to have to think about that. So this library is actually based on something called lineage-driven fault injection, which is described in a paper called Molly by Peter Alvaro, and unfortunately I forget the names of the other two co-authors, but Molly is like a tool that implements lineage-driven fault injection. What lineage-driven fault injection is that instead of testing a system top-down, where I'm going to inject faults at the top and then see what the output is, what happens is that execution of the system occurs and faults are injected, but then at the end it reasons backwards from the results to figure out whether or not the pre and post conditions that you expressed actually held, and if not, why. And actually another part of it is that the way that it injects faults is not by just injecting random faults in different places. It actually looks at the results and then tries to figure out, can I actually change the results by dropping a message or killing a node, and then checking that situation against those pre and post conditions again. And if it produces a fault, then you have a counterexample. If it doesn't, then it tries something else. And like I say here, fault-tolerant systems are ultimately about redundancy. Like when you really boil it down, strip out all the other terminology and stuff, what makes a system fault-tolerant is that if some failure occurs, some redundant path in the system is able to cope with that and resolve the issue anyway. So from the perspective of the system outputs, it doesn't matter whether that failure occurred or not. It doesn't change anything. But if you're able to reduce the system to those redundant paths and then eliminate those redundancies, whether a system is fault tolerant or not is dependent on whether or not the system upholds those guarantees with all support removed for the positive result, the output that you're desiring. More specifically, I guess, we'll get into it in a second. So what makes the system correct, right? The correctness assertions need to be, they can't be vacuous, which means like they can't be, I'm just going to drop every message that occurs in the system and oh no, it's broken. That doesn't mean anything. What you care about is under normal real world conditions, some set of messages are required to actually produce the right result. So the correctness conditions are based on something more realistic than just obvious things that are wrong. So this is what is meant by an admissible failure, right? An admissible failure is one that, like, okay, this is a thing that I will accept can happen. But you have to be fairly aggressive about that. It's not worth it to test things that are trivially correct, if that makes sense. So an example that I had here is, in Raft, is a follower grants a candidate his vote, and I guess maybe I didn't really describe Raft here, but there's 3 states in the system. There's a leader, candidates to become a leader, which occurs during an election, and then followers, which is like the default state of every node in the system. So when a leader election occurs in Raft, all the nodes become a candidate and say, I want to be leader now. And based on who is able to accumulate the most votes, a leader gets elected, basically. There's a little bit more to it than that, but I don't want to dive too deep into it. But the point is that if a follower grants a candidate its vote, it only gets one vote, right? It doesn't make sense to let a follower vote for everybody because you can never elect a leader that way. So everybody gets one vote. So if in an election you voted once already, it should never be the case that you voted twice. And that's something that makes sense, right? That's a fundamental property of Raft, and it's something that we want to guarantee is upheld. That's the kind of example of a pre and post condition, is if I voted, then under this execution, I never voted twice for the same election. It's something that we can test based on the execution trace that we've produced. The outputs of the system I mentioned, like lineage graphs and I guess I didn't mention Lamport diagrams, but that's what this is. Leslie Lamport came up with this diagramming format, which is a set of nodes, and then sort of like this incremental time-based expression of here's the communication that happened in the system, right? So this is actually a graph of a issue identified in Kafka using Molly, where what happens is there's, this is a Zookeeper-based system, right? Zookeeper stores a list of in-sync replicas, which is like members of the cluster that are up to date. In this scenario, the two replicas on the left, B and C, get disconnected, so they don't send their I'm up to date, like hello, how's it going thing to Zookeeper. So Zookeeper removes it from its internal ISR list, that in-sync replicas list. And so there's only one replica remaining, A there on the right side, and it elects itself leader, or it is elected leader. The client then performs a write after those nodes are disconnected. It's kind of the third step down there, which is acknowledged by the leader. But then that leader crashes, and so now there's no replicas up to date. At this point, that write committed, or that was, the client was told was committed, was actually dropped, like that data's gone. So no matter how the system recovers, that write will never be recovered. And this is something that was found and fixed in Zookeeper as a result of using this lineage-driven fault injection. And the way that it produced that is basically worked from like, this client makes this write and is committed and tries to figure out like, well, how can I make sure that the write is lost somehow, that it's not durable? Oops. So there's a few remaining things that I have left in Cadre for actually getting this released. The idea of Providence, so this is the lineage graphs, right? So I need to be able to say, given this value, what produced it. I've got that started, but I haven't finished it yet, and that's kind of the last major piece. And then also being able to eject a few different kinds of faults that I don't support yet, which is the idea of message delay and reordering. So I want to be able to generate tests that reorder events, make sure that the outcome in the system is still the same. And that's really important for consistency models where ordering is really important, where you want to verify that, like, regardless of the order of these operations, the output remains the same. I actually used Chris Keithley's Raft implementation. I changed things in it to make it work with Cadre's API, but I fundamentally left pretty much the whole thing the same. It was sort of my test to make sure that the API was actually something useful in a real world situation. But was able to run this and like verify some trivial properties of his implementation. His is not complete, or I mean, I haven't looked at it, I guess, in a couple months now, but I'd really like to finish what he's put together because I think it's probably the best implementation of Raft that we have so far, even though it's not fully complete yet. It's built sort of from this first principle of like, this needs to be correct above all else. And I think using Cadre as a way to verify that that's true will allow us as a community to say, like, we actually have an implementation of Raft that we can trust because we've model checked it. And to be fair, lineage-driven fault injection, I didn't really say this, it's not the same as like a TLA plus like model checking kind of thing. What it does is it exhausts the space of possible failures that could, cause a result that's not good. So it eliminates all those redundancies I talked about earlier. But once it's removed those, it knows that no other combination of faults can possibly have an impact on the output. So it doesn't need to test that space of problems. But it does test the full space of problems that can have an impact on the outputs. So this makes it run super fast. Not only are we kind of mocking out time and everything else so we can run it as fast as possible, but we can also exercise the full space of faults to make sure that something is model checked to the extent of, we ran this simulation for, theoretically like 1 year and it never produced any faults under various combinations of reads and writes. It doesn't actually take a year to run it, but the point is that you set some sort of finite time at which you assume that the system is good. It needs to be long enough for the guarantees that you uphold to actually be meaningful, but like if you say that with 5 minutes of execution, this set of faults, no fault was found, that's not necessarily going to tell you that, well, in minute 6, a fault occurs that doesn't break the whole thing, right? So that's why it's not the same as a true model check, because we don't say for unbounded lengths of time, this is true. We put a bound on the amount of time and the number of faults too. Because again, like I was saying earlier, where if you just drop all the messages that occur, then sort of trivially prove the system fails under that condition, but it's not meaningful. And then I also, as part of developing this, worked on a causal plus consistency model. Like I wrote this library Swarm that was based on a pretty naive approach to trying to build a eventually consistent replicated process registry to meet needs I had at a project I was working on. And it's not correct. Like it's good enough for production in the case that I was using it in, but I don't like the fact that it's not correct. You know what I mean? So this library really kind of evolved from my need to say like, okay, I am confident that I actually did this right. And I didn't mention CRDTs, but in the last talk those were brought up, and that's not really important to Cadre so much as relevant to a consistency model that you'd build, right? So if you're expressing replication in terms of CRDT, then you want to be able to verify that the outputs produced by how it resolves conflicts are what you expect them to be. So anybody that's working on some consistency model implementation is going to care about these same concerns. So I started working on the causal plus one just as a way to vet that this was going to work for my particular use case, but I need to finish that up. And then this last note here about parameterization, what that means is that you define the time bound, the type and number of failures that you're going to allow to occur, kind of this concept of end of finite failures in the Molly paper, which just defines the point at time at which you're going to stop injecting failures and let the system try and recover. All that stuff you have to do by hand right now, but really should be automated, right? The big thing that you'd want is to be able to write property tests using like proper or something and let it just sort of automatically generate the parameters for this and verify that under some like 10,000 tests or something that the system held up under these different variety of failures. Because you're not going to necessarily be able to predict what set of failures will produce the problem that you care about. You need to randomize that. So that's the other part of this that I need to add. Unfortunately, I kind of like rambled here a little bit. I know that this is maybe like a curvy path to get to talking about Cadre with going through all the terminology and stuff, but I felt like that was important to kind of lay the groundwork of what this tool is trying to solve. But if you have any questions about any of it, feel free to come and talk to me. But that's basically all I had for now. I think we have time for questions, maybe. I don't know what time it is.
Yeah, we're out of time. But,
okay, yeah.
Appreciate that. We're all looking forward to when Cadre gets released. So.
Thank you very much.